So I'm hoping you guys recognize numbers 1 and 2 as being really nice review questions, and we'll start thinking about quiz tomorrow when it comes to relative extrema and absolute extrema. Those could easily be 2 questions on your quiz tomorrow. I went ahead and said f prime of x is 0 at all 4 critical points. That kind of sets me up for success for any reasoning that I want to use later on. I said, hey, these are all critical points. And then I go on to say that x equals -2 and x equals 3 both have the same characteristic of f prime going from negative to positive. So I can kind of combine those 2 into one statement. And then kind of a similar idea at x equals 1 and x equals 6, because f prime changes from positive to negative at both of those x values. This is a good example of the first derivative test. This is a good way to have done this one. Hopefully you've been practicing your wording on how you justify things and that good first derivative test type reasoning. Any questions on 1 or any concerns or contributions, comments, any of the above? What can I do to help you with number 1?
We're still wrong. Yes, we are. No, we're still wrong. We're still wrong. Because we didn't have the end.
You can see number 2 up there also. Number 2 specifically mentions absolute extrema on the interval from -2 to 3. So the way that I handled that is I collected my candidates. My candidates were the endpoints of -2 and 3. And the critical points of -2 and 1, and it just so happens that one of the critical points is also an endpoint, right? Kind of a coincidence there. I would not say that there's any pattern to be pulled from that. And then I tested to figure out which one was the max or the min by simply taking those candidates, plugging them into g of x for the input, and then the outputs told me all that I could do to them. Any questions on 1 or 2? Yeah, Caitlin.
Why is 1 0? Why is it when x is 1, y is 0?
See if I messed up my arithmetic. I'm open, it can happen sometimes. So what I...
Oh, wait, never mind.
Oh, you were plugging into g prime.
Yeah.
Yeah, so if you said g prime equals 0 and get a number, and you plug it back into g prime, you better get 0. So this is where people get confused. If you bring up a really good point. When you are testing for absolute extrema, you want to take all of your candidates and test out the y values. And the way that you test out the y values is to plug your candidates in for the input of g of x or f of x or h of x or whatever. But if you're doing the first derivative test for relative extrema, you want to test out the intervals on f prime or the intervals on g prime. And so then you're going to be plugging in numbers into g prime and saying, hey, look, g prime went from positive to negative. Therefore, that kind of thing. Yeah, so like figuring out what goes in, what gets plugged into what, it's really important to understand what does my output mean. And if you remember g prime, that just means slope of g, versus g, which is just the y value of g. If you can like get that solid, even if you kind of get forgetful or something, or you get confused, you can always think, okay, what does the output mean? And if you can be solid with that, you should always be able to reason your way back to what do I need to do. All right, no one's knocking down my door saying I got questions or comments or concerns or anything. All right, so here's Nate, yes.
So when we say max and minimum, we don't have to list the x value or anything.
So the way this one's worded, yeah, it just says what's the absolute extreme, what's the absolute max, the absolute min. We're talking about y values. If it does say, give the point where the absolute maximum happens, or give the x comma y for where or maybe it just says give the x value for where such and such happens. Just carefully read what's asked for.
Okay.
This is a pretty common wording, though, where you would just give the output value.
Okay.
So if I said, Nate, what's the most you've ever weighed? You wouldn't say June 2nd.
Yeah.
You'd say 100 and whatever pounds. And then he started working out, and it was like 210.
Yeah.
Whatever. Okay. Here's number 3. So number 3, this is a water tank question, right? We have a rate of golf balls landing on the grass, and then we have a rate of golf balls being removed from the grass at the driving range. So I did L of t minus 9 equals 0.
Set it up right, I just can't use a calculator.
Do you guys agree with that number?
No.
Oh, no. Did I mess something up? What do you guys think it is?
I got 7.68 as well.
Okay. Man, I don't know. Kind of a complicated expression. Maybe I messed something up. It's been about 7 months since I did this one, so it's not exactly fresh in my mind. So you guys think that t is something else? Let's find out. So t you think is, say again, 7 point something?
7.680.
680. Sounds like there's kind of a preponderance of evidence that that's. I'll trust you. Like I said, this packet is only 60-something pages long, and I did every single one of them. So I might have pushed the buttons wrong in the calculator. I'm willing to accept that. So then I'm willing to bet then that this would be the same pattern, though, right?
Yes.
It would just be that we get this sign change on our net rate from negative to positive at 7.680 instead of whatever that other number was. Okay. So as long as you see that sign change at that critical point from negative to positive, that means you would have a minimum number of golf balls at 7.680. Okay, so details with numbers aside, concept-wise, what do you think? Any questions like why is it L of t minus 9? Why isn't it 9 minus L of t? Stuff like that. Do I need to show this? Why is that important? Is that not important? Anything. Let me know how I can help. We're doing good on time. Let's not rush. Do y'all see how this, like, why I would call this like a water tank question? Rate in minus rate out. I mean, it's golf balls and it's grass, but it's still rate in minus rate out. Or maybe this one should be rate on versus rate off, right? As far as on the driving range versus off the driving range. Whatever. Okay, so you're totally fine, or you're thinking of a question. I want to help you if you need. Okay. Apparently I needed help pushing the buttons on the calculator. I'm going to try that while you guys are working on something. Okay. So, how to go with the whole antiderivatives big list? The good news is, like, that's kind of the whole list. And we'll spend a big part of Unit 5 perfecting your skills with that stuff, okay? So we're going to start off today with some relatively easy exercises. And I say relatively because this is brand new. So we're going to keep this. Oh, sorry, did I mess you up there? I'm making a video. You could always go back and screenshot the video if you wanted to. That's not it. Where did you go? That's not it either. There it is. Okay, so y'all see I sent out some solutions to those, the list. Hopefully you saw that update. The one thing I wanted to discuss real briefly here before I just set you guys off on your path for a few minutes here. Does anybody know why the plus C was necessary? Like, why did every single thing I put on there have a plus C on the end of it? What do you think, Reese?
Because when you take the derivative of a constant from 0, so when you're taking it parallel, you're going backwards.
Yes.
And derivative, you're going backwards. So we don't know if there was a constant there or not.
So let me give you an example. Like if I said, what's the antiderivative of 2x? Just, you're asking yourself, what expression would have a derivative of 2x? What would you say? X squared. It's just reversing the power rule. So we could say that this is equal to x squared. But if your partner said, I think I disagree. I think it should be x squared plus 9. It's kind of hard to debate with them, isn't it? Because if you just did the derivative of the result, wouldn't you get the exact same thing regardless of which one you picked? Same thing if somebody did a subtraction, right? Integral of, or the antiderivative of 2x dx, you could say is x squared minus 10. Again, it would be very hard to argue with that person because if you did the derivative of that, you'd end up, in all cases, you'd end up with 2x. And so these all have a derivative of 2x. And so that plus c is exactly what Reese said. Since we're reversing the derivative, we have to acknowledge that the derivative of a constant is 0. So there could be any arbitrary constant added onto the end of it, and it would still make it an antiderivative. And so we acknowledge all of those possibilities with a plus c. Later on in Unit 6, that plus c will become even more important than it is right now. So don't forget it. Definitely don't forget it now, but it'll ramp up for sure when we get into Unit 6. Okay, so please do include that when you're working on these. So I want you guys to try the left column. And let's discuss, let's talk. Let's get any confusion out as best we can before we move on. Well, please try that left-hand column. And you can let me know what you think. So the first one, I noticed that 5 is a constant multiple, right? It's a 5 times some variable expression. So the first thing I could do here is write 5 antiderivative of x dx. Just get that right outside the antiderivative. Sometimes this is super key. Sometimes it's not going to seem like it matters that much. Others, it's going to be a big deal. And then the thing I've got to do is I've got to look at my integrand, which is the expression in the antiderivative there. And I've got to think to myself, what form is this? So I'll give you some ridiculous ones. Is the integrand a form of e to the u?
No.
Definitely not. Is it a form of sine of u?
No.
Definitely not. Is it a form of u to the n? Yes. It's a variable base with a numerical exponent. And the exponent's not written, but we all know it's a 1, right? So this does not fit sine. It doesn't fit e. It doesn't fit natural log. It doesn't fit any of that stuff. The form is really crucial here. It's x to the n. So the strategy that we select is the reverse power rule. The reverse power rule, you'll see that on the previous page. And the reverse power rule requires that we add 1 to the old exponent. So that would give me x squared. And we divide by the new exponent. Of course, that's 2. And then we always add c. So if you wanted to, you could write this as 5 halves x squared plus c. And that would be your final antiderivative for number 1. Quick question. What if you were doing stuff like this, you were doing number 1, and you thought to yourself, man, I think that's right, but I'm not sure. How could you check? Just do a derivative. And if you get what you started with for your integrand, then you must have done it right. That makes sense? Okay, number 2. Number 2, I want to tell you, for most of our class, if we can algebraically and logically avoid a fraction, that's exactly what we're going to do. Okay, so like a question like number 8, which we haven't gotten to yet, we can't really avoid those fractions. But in a setup like number 2, it's pretty easily avoided. I would recommend that you take that integrand and just change its form by flipping up. And when I flip up, I get x to the negative 4th. What form is this? Like, what pattern does this fit? It's the u to the n, right? It's the variable base with the numerical exponent. So we would actually, for number 2, follow the same rule, follow the same pattern that we did with number 1. So I would add 1 to the old exponent, and I would get x to the negative 3. I would divide by that new exponent, so I'd divide by negative 3, and go plus c. And of course, I could rewrite this as negative 1/3 x to the negative 3rd plus c. I could move that x to the negative 3 around. I could put this in a number of forms, all of which would be just fine.
So on the equation sheet, it says that 1 over u is equal, or 1 over u du equals ln of u plus c.
Yeah.
So if we use that here, just at the...
Oh, that's the thing, though, is 1 over u du. The du has to be the correct du. So it would need to be the derivative of the denominator. I'll show you. So we should be able to check this, right?
Yep.
So on number 2, if I said, hey, I think the answer should be ln of x to the 4th, I should be able to differentiate that and get what I started with. This would be 1 over x to the 4th times 4x cubed. That would give me 4 over x, which is definitely not the original.
Okay.
Yeah. So the derivative of the denominator has to be the numerator for it to be ln. And you can, we'll see one of those here in a little bit. So it's going to be tempting at times when you get a hold of stuff like that to say, man, whenever there's a fraction, it's got to be natural log. Not true. Sometimes it will, sometimes it won't. It all depends on form.
Okay.
Okay. Number 3. Again, if I can avoid a radical, I'm going to definitely avoid a radical. I would rewrite this as x to the 1/2. And so now can you see, I hope you can see, how number 1, number 2, and number 3 are all, they're different, but aren't they all the same form? Aren't they all x to the n or u to the n? Like some variable to a numerical exponent? So I'm going to use the exact same pattern here. This is going to be x to the 3/2 over 3/2 plus c. You will probably never catch me writing that. I'm going to automatically copy dot flop these. So I would write this as 2/3 x to the 3/2 plus c. The thing I wrote first is just fine, but I usually will get to that form. Okay, so how are we doing? That's kind of like a run of 3 in a row with the power rule. What do you think? Okay, so then let's take a look at number 4. Through 6. So do you notice how numbers 4 through 6 decidedly different feel? Do you see how numbers 4, 5, and 6 there are no x to the n's? I look at number 4 and I think, what's kind of the overall flavor of this one? It's clearly a sign, isn't it? So I've got a constant multiple, so if I wanted to, I could bring that out. So it'd be 2 sine of x dx. And then as long as I can remember what the antiderivative, bless you, of sine of x is, I'm good, right? So what's the antiderivative of sine? It's the opposite of the derivative, right? Yeah, so it'd be 2 times negative cosine of x plus c, probably better written as negative 2 cosine of x plus c. And I'm done. You can always check this by doing a derivative, and hopefully you get a happy result. Okay, number 5. For the first time, number 5, we have an integrand with 2 terms. So I'm gonna overkill this one a little bit. I don't really have to do what I'm about to do, but I'll do it anyways. What you can do is you can actually split this up into 2 separate antiderivatives, like so. Just like we can split up derivative terms into just term by term by term differentiation, with a sum or a difference, you can do this. You cannot do this with a product, but you can definitely do it with a sum or a difference. Okay, so the second one is probably the easiest one, right? What's the antiderivative of e to the x?
E to the x.
E to the x, yep. Okay, so we'll put the plus c on there. The first one, there is a rule for this. It's the antiderivative of a constant. But just think for a second. Like, hopefully this will make logical sense. If the derivative is 5, what would the function have to be? 5x, right? The derivative of 5x is 5, so the antiderivative of 5 would have to be 5x. So this would be 5x minus e to the x plus c, and I think I would just leave it in that form right there. Okay, the last one in that column. I could pull the 3 out because it's a constant multiple. And then this one just comes down to, do I know what the antiderivative of cosine of x is? And the answer is? Say again? Sine x, yeah. So this would give me 3 sine of x plus c. Again, in every single case, especially this left column, it's not too hard. You could always do a derivative to double check to make sure that you didn't make any silly mistakes. You should feel pretty confident at that point that you've got it pretty solid. Okay. 1 through 6. If you haven't already looked at the right-hand column that goes 7 through 11, please do. Okay, Jed, what's up?
For 5, would it be plus 2? Why is it not plus 2C?
Good question. Hey, if anybody's curious, Jed's question is a good one. He said, why is, in number 5, why isn't it not plus 2C? So let's think that over. So if I did this and I said, the antiderivative of the first one is 5x plus c minus, this would be, I think we could argue actually a different way if we wanted to. Wouldn't it be e to the x plus c there? Okay, so then you would say, well, then why wouldn't these c's combine down into maybe even being 0, c minus c? The thing of it is we know that c is some unknown constant, and the other c is an unknown constant. Do we know if they're the same c? We have no idea. So in this case, an unknown constant minus another unknown constant is just some other unknown constant. So we just leave it as a c. Same thing if it was plus, right? So c plus some other c, or maybe even the same c, we don't know. It would just be another constant. So customarily, we won't write that step. We'll just say, hey, all of those c's are collected as just a single c at the end. But your question's valid for sure. Yeah. Thanks for asking. Anybody else with a thought or a question like that? Anytime you think, I think it should have gone that way, but he's telling me it goes that way, that's like a lead-in for a question. I hope that you'll ask somebody. I'd love to answer it, but maybe a friend could too. So we'll take a few minutes here and get as many of these done as you can, then I'll get through some answers as well for this right side. There's a couple that I for sure want to get to. I'm not as concerned about number 11. Number 11 is a lot like number 2. 7, 8, 9, those are really good ones to talk about. We have a cat and hat game. Cat and hat game is, you know, all the stuff the cat does in the story. Have all these little props, like a little fish bowl and a fish and the mom's dress and all that junk. And you play these little cards, and so you're supposed to hop on one foot with mom's dress on your head. And if you can do it, you collect the cards and stuff. My kids love that. So we play a lot of cat and hat, so it's a good time. Let's take a few more minutes to get as many of these done as we can. Remember, antiderivatives are largely about form. You've got to recognize the form, recognize that what you have in front of you is the derivative of something.
Which other one is okay? So
What do we got?
This one, if you switch it back to
You end up with a major problem, don't
yeah, because then it becomes 4 over 0.
It's the exact same with the other one too. This,
you? You end up with division by 0. And really, on number 8,
Yeah, I was saying because we were talking about the first part. I was like the second part does the exact
Wait,
same
so
thing.
when it turns out to be division by 0, is that when you take the LN?
that's a hint that it's going to lead you right to ln. Yeah. Anytime you're like, I need to divide by, oh my gosh, 0, you should go back and think, wait a minute, maybe this was natural log. Yeah. Yes, ma'am. Maybe just another minute. I want to max our time out here, but I want to give you a chance to get as done as you can. Okay. So let's talk about number 7. If we could do 7, 8, 9, that would be really, really awesome. I'm less concerned about 10 and 11 because we've more or less done those already. So number 7, what I went ahead and did ahead of time is I split up the integrand. Since it's a sum, I can just consider term by term. So the first one, people will mess this up all the time. I want you guys to check this out. I'll see people that do this. They'll look at that first term and they'll say the antiderivative, bless you, is 9 to the x plus 1 over x plus 1. They'll treat that like a power rule, but it is not a power rule. Remember, the power rule is variable with a numerical exponent. This is an exponential, right? This is a numerical base with a variable exponent, so it is not this. What I need to do is remember what the form is, what this looks like. This ends up being 1 over ln of 9 times 9 to the x, which hopefully would make sense knowing you know the derivative of 9 to the x, right? This hopefully makes sense. Now the other one's a little bit trickier. Remember, antiderivatives are very often about recognizing form, and I'm really hoping that when you looked at that second term, you thought to yourself, that looks a lot like something. Did anybody identify that something? Say again? If you try that, you're going to end up with all kinds of issues when you check. There's going to be chain rule. There's going to be a chain rule mess all over the place. So yeah, this one, that doesn't work very well. You'd find that in your check if you did check it. It should look like something. It should look like the derivative of something. What do you see? I think you said something.
The arc sine of 1 over x.
This is inverse sine, is it not? Remember? U prime over the square root of a squared minus u squared. Recognizing form is huge. So this would actually end up being arc sine or inverse sine of x, and then don't forget your plus c. So I see this, kind of like I suggested with your derivatives, as a prime opportunity for flashcards. I really do. I think you should flashcard these just to get a lot of practice, a lot of repetition. Because isn't the only way that you recognize something is if you see it a lot? Right? I mean, if I threw one of you out on the basketball court and I said, hey, I need you to recognize that the other team's in zone defense or man defense, I'm guessing Nate could do that. Others might, but if you've never played basketball, you don't even know what I'm talking about. But if you've seen zone defense over and over again, you're like, oh, they're in a zone, let's get into this offense, right? You need to see it a lot. So you need to see these a lot. Number 8. Number 8, again, we'd split this one up. 4 over x dx plus the antiderivative of 1 over 1 plus x squared dx. I get the 4 out of there. And once I get the 4 out of there, I'm hoping that knowing what you wrote down already, you would look at that antiderivative of 1 over x and say, I know exactly what that is because the derivative of blank is 1 over x. ln of x, right? So we curiously here will include absolute values as part of the input, and we'll get into why that is later. I need to include my 4 here. Oops. But you do want to have absolute values there. Don't stress about the y yet. We'll get into that. And then by any chance, does anyone recognize the form of the second integrand? It's arctan. There you go. So it would be plus arctan of x, and then don't forget your plus c. The last one on this screen is very dependent on form. You look at this and say, all right, the 4 can come out. But then really you've got to recognize that secant squared of x is the derivative of something. Say it again. Tangent. So the antiderivative of secant squared would have to be tangent. So here you'd get 4 times tangent of x plus c, and you'd be all done. You see what I mean, where it's form dependent? If you look at it and you can't connect derivatives with these, it's going to be a struggle. We'll get into a lot more details as we go. This is merely day 1, and we'll spend like most, if not all, of January on this too. So you guys have a wonderful day. I'm excited to take this chapter's journey with you. Should be fun.